Well, here's take two of my notes for the day because my 40-minute Zoom meeting, when I ended it, it wanted to update, and then it never saved my recording. So, we have igneous rocks and metamorphic rocks and sedimentary rocks. What we did last week was go over some of the information, the very basic information, like this probably might have been the only thing you knew about igneous rocks. They formed from cooling lava and magma. So we have two types as far as how they formed and how they cooled. So we have extrusive, which you want to think exit outside. They've left the volcano. So they're extrusive igneous rocks. Since they're on the outside or the surface of the earth, which is quite cool, that doesn't insulate anything. And when I mean cool, I mean compared to magma, it's very cool. So they cool quite quickly. And because they cool quickly, crystals don't have a lot of time to form. So a crystal needs to have time to get big. So if it doesn't have the time because it cools quickly, you're going to have small crystals in these. So these are things like basalt, which you'd be hard pressed to find a decent sized crystal in basalt. It pretty much just looks like a black chunk of rock. Pumice, that's the one that floated last week in my notes. It has a bunch of air pockets in it. So air pockets are a clue that it's an extrusive rock as well. And then obsidian, it's glass-like, so if it cools super quick because it contacts water, it's going to form glass, which have literally, you can only see these crystals underneath the microscope. And I've looked at them before when I was doing some research for some archaeology labs that were trying to find obsidian to prove that there was trade going on between some indigenous tribes. So we had to sort through a bunch of little tiny dirt, you would probably call it, and you had to look for obsidian. So you were looking for little tiny chunks of glass that had black lines in them, and that was the obsidian. So intrusive igneous rock, they cool slowly. They are inside or intrusive to the earth. So they have layers of rock over them. So this would be like the magma chamber of an old volcano that no longer erupts, cooling off over time. So it's completely inside the earth. It's got a cover over it. It cools pretty slowly, and this allows bigger crystals to form. So this is like granite and diorite. So I'll go to that in a little bit here. Then the other way that they determine what kind of igneous rock is formed is what it's made up of, so the composition. So if it has a lot of magnesium and iron, they call it mafic. So magnesium and iron, Fe, ferrum. I think it has to do with the combination of both of those, the word itself. So they're darker in color because of magnesium and iron are darker. And this would be things like obsidian, which is black, salt, which is black, gabbro, which has got a lot of black minerals in it. Right. Felsic, silicon, or feldspar, which is potassium, I think. They contain a lot of silicon. They're lighter in color. They're things like rhyolite, granite, and pumice. So if we take a look at granite and we get a decent view at some of these things, you notice there's a lot of pink in here. That's feldspar, the mineral feldspar. And then occasionally, I don't know if there's much quartz in this one. There is, but it's really hard to see on that webcam. If you see any of the lighter colored stuff, like white, probably looks a little bit light gray on this webcam view. That is silicon or quartz. Okay, so if we take a look at the ID chart here and we go to the igneous, you'll notice that this whole chart has to do with those two things we just talked about. How fast did they cool? And what are they made up of? How light in color are they? How dark in color are they? Okay, so slow cooling, we notice we can actually see the different crystals that interlock like puzzle pieces in these ones here. So lighter colored and has big crystals is granite. If it's darker in color, it's got a lot more dark mafic crystals in it, but they're big. Then you have gabbro, sorry. If you can barely see those crystals, you're going to have a faster cooling rock. If it's lighter, it's rhyolite. If it's basaltic, if it's basalt, it's got a lot more iron and magnesium in it. Right. And then there's some that have air bubbles in them, scoria and pumice. The difference is what is made up in those. More silicone and pumice, more mafic stuff and scoria. These are like the red lava rocks is scoria. And then obsidian is glass, volcanic glass. Right. So that's some of that stuff there. Which brings us to the sedimentary rocks. So sedimentary rocks should make you think sediments dissolved, or not sediments, mineral dissolved. Oh, that's what I'm reading the wrong thing. Sedimentary rocks in general are ones that are formed by sediments, but we're going to see that's not always the case in some of the types down below. But the two words that were on the rock cycle last week that I probably explained what they were, but we didn't write anything down about them. We have two processes that can hold a sediment together. One is cementation, so cement or glue. So if you have a mineral that dissolves in water and then works its way into all the little sand particles, and then it solidifies and holds those sand particles in place so they can't move, you have cementation happening. So limestone is a really good mineral that can dissolve in water and work its way into particles of sediment and then undissolve, so solidify essentially, and glue those things together. If you've ever been to a cave, chances are good that it was probably a limestone cave. So all those fancy features inside a limestone got eaten away by water over time, and then like the stalactites and stalagmites form from the minerals dissolve or not dissolving, undissolving, and forming those structures. Compaction is pressure pushing rock fragments or sediments together. Just a minute, Daddy's got to do this video so he can get it on because it didn't work. Then I'll make lunch, okay? So compaction is compacting things, so pressure squishing rock sediments together. Okay. So we have three different subcategories of sedimentary rock here. We have the one that I would say is what you would think of when you think of a sedimentary rock. It's called clastic rocks. They're made up of the really fancy word for sediments in geology is a clast. So they've either been cemented together, glued together, or squished and compacted together. Right. Then some of the stuff that helps you know kind of the history of the particles in them. If the chunks of rock that you see in them are rounded, you can know that those have traveled farther. They're older, so they've been around longer and had more chances to get worn away and rounded. Or they've spent a lot of time in rivers, oceans, lakes, things like that. So the best example of this that I can think of from my experience is Lake McDonald or Lake St. Mary's. These are both lakes in Glacier National Park in the mountains. So they have tons, like the bottom of the lake, at least the bottom that you can see, is just round, flat rocks, like rounded edge, flat rocks for as far as you can see. It's like literally the perfect skipping rocks everywhere. So I know that those rocks have been around for a long time. They probably broke off in the mountains and have since kind of worked their way down towards this lake in spring runoffs, like when it's kind of flooding and all the snow is melting. So there's a lot of force in the river to move rocks. And they've moved of fairly good distance away. They're older and they didn't break recently. But if you go up to the top of a mountain, you're going to see that where maybe a glacier was there a little while ago, or the snow and ice, when it melted and froze again, kind of cracked apart the rocks. You're going to notice that they have much more jagged edges, pointy edges, blunt edges. They're not nice and round. And that lets you know that they are freshly broken when you see that. And they are younger particles. They might be really, really old rocks, but they're young in terms of um, how long ago they broke, I guess is what I mean by older and younger. Okay, then we have chemical rocks. So rock salt, I don't think I've showed this one yet. This one, you notice, has got very square cubic edges. So sodium chloride forms cube-shaped crystals because the atoms stack up in cubes. And this is formed if you have salty water and that water evaporates, you're going to have rock salt form, solid form of salt. Now, if I took this and I smashed it with a hammer or ground it with a mortar and pestle or something, I'm going to form tiny table salt crystals, which you'll notice if you look close enough at your salt, it's also little tiny cubes. Right. Then biochemical rock. So really big thing here, bio meaning life. It's made up from old dead skeletons of things. So typically this is marine life. So seashells, whether it's a clam, a snail, anything that's got a calcium carbonate shell, is if enough of them get kind of accumulate, I guess, or gather, settle on the seafloor, the lake shore, anything like that, you're going to form a big enough layer that they're going to get cemented together, and you will form around here. We have tons of limestone. Like if you go on any of the rivers or places where you can see exposed cliffs around here, sometimes along roadsides where they literally dug through the road or through the ground in the rock, you'll see limestone. It's one of the most abundant rocks around here that formed here instead of getting brought here by a glacier. And then there's coquina, which is, I don't actually have one of those in this rock set that I have, but what I remember from my last school's one is it was literally like you took a bunch of seashells and you glued them together. You could see shells literally inside of them. Okay. So clastic, what you typically think of as a sedimentary rock, it's made up of sediments. So that's sandstone, siltstone, claystone, anything that forms from sediments or what you would probably call dirt getting glued together. Chemical rocks is when things like salt get left behind when water evaporates. And then biochemical rock is living things dying and forming a thick enough layer to form rocks. Right. Metamorphic rock. So it gets a little crazy here. I've got some lines to kind of help separate things out. But metamorphic rocks are formed when rocks undergo heat and pressure. So they are why is it frozen? Okay, they form from current rocks. Like there has to be a rock already made for it to go through metamorphosis. You can't, like, igneous rocks form from magma, which aren't rocks. Sedimentary rocks, for the most part, form from sediments, which are tiny rocks, but they're not really what would be called existing rocks or parent rock like we have here. So metamorphism is just rocks change shape. Their mineral composition can change. This does not mean that like their elements are created or destroyed. It just means they're rearranged so they can form different chemicals. Okay. And then their structure changes too, so they might form layers. Plastic deformation is when we smush warm rocks together and they bend like plastic. So you can kind of move them around like modeling clay, would probably be a good example. The parent rock is the original rock before the metamorphism. So if we think of limestone, limestone is made from a bunch of small particles of dead ocean organism shells, that calcium carbonate. It's not super shiny. It's not the hardest rock in the world, but if you put that rock, that limestone, through heat and pressure, you're going to form something much harder, much prettier, much fancier, fancy enough that lots of expensive buildings or sculptures are made with it. You're going to form marble, which comes from the parent rock of limestone. Okay, which is definitely not this white. It definitely doesn't shine, and it's not as hard as this one. So that's what the parent rock is. What was the rock before it went through the heat and pressure? Okay, and there's pretty much kind of a set path for some rocks. Like if you have shale, which is pretty much, I think, like clay particles smushed together and stuck together, and it goes through heat and pressure, you're going to form slate. So you've got layers in slate, you can break it apart. It's got a little bit of a sheen to it, a little bit of a shine. Where slate, I wonder if I've got, no, this is slate. I mean, this one is slate. I don't know if I said shale. Shale. Slate. Right here. I had it here already. Okay, so let's compare them side by side here. This is a decent sized one here. So they look pretty much the same. I've got in what looks like my right hand, I've got the metamorphosized one, the metamorphic rock, which is slate, the one that they used to make chalkboards out of and whatnot. You can see some really distinct layers, that it's even broken apart into those layers. I don't know if we can, when I'm rotating these back, obviously they both, it's backwards for me. They both reflect light, but you can notice that we've got a definite little bit more of a sheen or shininess on the slate, which was one hint that this is metamorphic, is the shininess that they tend to get. And there's even some versions in here that are even shinier, like here's two side by side, but these are both slate, but you can see that this one right here, and maybe you can't because it's not on the screen, is a little bit shinier. Probably hard to do over the video, but I can see little sparkles. It's kind of glittery when I look at it. Yeah. So glitteriness is a hint that it's a metamorphic rock. Layers are a hint that it's a metamorphic rock. And if we take a look at some of that stuff here, I'll be writing it down at the bottom here with foliated and non-foliated, layers or no layers. But before we get there, we've got contact metamorphism, which is caused when magma heats things up, not quite to the point of melting, but it's the cause of the heating instead of just being deep in the earth. If magma shoots up through a layer of rocks, it's going to cause the ones around it to form metamorphic rocks because it heats them up. Regional metamorphism is more of a large scale process. So a large area undergoes heat and pressure because there's things happening that create a lot of heat and pressure. So mountain building, when two plates smash into each other, you're gonna pile up rocks and get deeper, and you're gonna have a lot of pressure on some of the rocks in the bottom, a lot of heat. And then as more plate tectonic stuff happens that pulls them apart or pushes things up more, or erosion happens, you're going to have some of those rocks get exposed on the surface and you can actually see them. Right. And we have our foliated and non-foliated rocks. So foliated form layers and elongated crystals. So they're slates, gneiss, and schist. Schist was one of the ones that I actually haven't seen laying around in my boxes, but schist was a cool one. You could see the layers in it. And the one that I had actually had perfectly formed crystals in it. It had little rubies, if I remember correctly, that were like stuck in the side of it. But we had the slate, which had layers, and here's gneiss. So if I get that close enough here, you can see the layers of light and dark crystals. They're not just randomly interspersed. There's literally a light layer and then a dark layer and then a light layer and then a dark layer. So that's a foliated rock. Non-foliated, the best example that you've probably heard of is marble. So marble doesn't have layers, but it does change its properties quite a bit. It gets more glittery looking, which is hard to see on this webcam because it just kind of looks like a bright white rock instead of glitter. So marble is probably the best example there. Let's take a look at this point at some of these ones. Hey, where it fell. Yeah, I'm guessing that no one's heard of quartzite and Hornsfell. Gneiss, I showed an example of, or gneiss. Schist is another one, but it's not light and dark. It's just all pretty much dark, if I remember correctly. Slate is the one that we were looking at, and then we have marbles. So pretty sure there's more metamorphic rocks than this, but this is just a good one for middle school classes or ones that you might have in a classroom. So we take a look at sedimentary rocks, siltstone, sandstone, those make sense. They're made up of silt and sand. Shale, coal, rock salt, gypsum, which we make sheetrock out of. And then there's a bunch of different versions of limestone or coquina, which is just big chunks of shells. Okay, so there's some of the different types there. Then what I want to go over here briefly is if I kind of alternate back and forth between this sheet here and making this full screen. I think I can make it full screen. Or I just made it go away. Well, that's no good. Yeah. Back to tab. Okay, apparently I can't make this bigger, which is what I was trying to do. So, yes, I can. Let's alternate back and forth. That might be as big as it gets. Okay, so here's a rock that we haven't seen yet. I haven't even showed it or named it. But if we take a look at this rock here, what I want us to notice is, yeah, it's a little bit better focused. Right over here, I notice that I have what looks like a pebble. Like I walked out onto a playground, grabbed up a piece of pea gravel, and shoved it in a rock. I've got, oops, this way, another one. This is super hard. Doing stuff in a mirror. Okay, so there's another one right at the tip of my fingertip there, another little pebble. But it's kind of got a bunch of sandy particles all around it as well. So if I feel this, it's rough. It is fairly, if I can capture that on here, but it is pretty sparkly. There's a few sparkles you might see occasionally. Okay, so if I take a look at this then, Okay, so the first thing you got to do if you just go out and walk around and pick up a rock and you can see it fairly decently, it's pretty clean and whatnot. The first thing you got to do is figure out which type of rock it is. So what I've got here has fossils or large sediments, has a rough plastic feel, some absorb water, no naturally formed crystals in them unless they are sediments like sand. Okay, so that's kind of the things you would want to look for sedimentary rocks. Igneous, some have large crystals like a granite countertop that interlock. So they wrap around each other, they break apart or won't break apart easily. Some have very small crystals, but they still have crystals that interlock. Some are glass-like, some have air pockets. Those are pretty dead giveaways as to that it's an igneous rock. They do have shiny crystals, but it's not quite the same as metamorphic. I would describe metamorphic shininess as glittery. Weirdly, this rock I'm holding is glittery as well. Oops, the rock I'm holding is glittery. But let's take a look at metamorphic. Most tend to be very shiny, like glitter. Some, not all, have layers. I don't see layers on this one. I do see the glitteriness. Some have perfectly shaped crystals that form in them, like a really cool looking quartz crystal or a little literal ruby sitting there that looks like someone from a jewelry shop can plop it into a ring. Okay. Now, so I did have glitteriness, but it's rough feeling. It's gritty. I can tell that there's some sand that's made up in this thing here. I saw large sediments. I can see the sand. I can see, where is it at? This big guy here, that big pebble. So even though it's glittery, since I've got more stuff in the sedimentary part, I'm going to say that this is a sedimentary rock, which if you see sediments in it, that's pretty dead giveaway. Like maybe this side you can see more sticking out there. Okay, there's one literally sticking out right tip there, a darker colored one. Okay, so once I know what type of rock I've got, I go to that page and I look at kind of this key. So keys give you like some options here to go through, and there is one weird thing that happened with this rock that is going to be an exception, but there's often exceptions in the world, unfortunately. So the first thing that it wants us to do is test with acid. So if I get some hydrochloric acid, what I'm looking for in an acid test is bubbles. So just like baking soda and vinegar, if acid reacts with calcium carbonate, which is in limestone and coquina and things like that, it's going to give us a clue as to what's in it. So let me get this situated so you can kind of see the top. Okay, this is the weird part. Oh, maybe that's what it is. It only bubbled once it hit this little orange chunk there. It didn't really bubble on the other's part. So I'm guessing we have a chunk of limestone in there. That's why I'm getting bubbles. I didn't think about that. But if I put it other places, I don't get a reaction with it. There are a few bubbles. There are a few bubbles, but not many. I'm on right back. So definitely that orange chunk, the rusty looking piece that's in here, it's definitely got some limestone in it. It bubbled furiously when I did that. But otherwise, it was a pretty neat reaction, and I'll walk through like why I'm going to say that saying that it reacts with an acid is not the best idea or best diagnosis is the word that's coming to mind right now. Best identification process to go by and we might actually kind of go against what we saw. So if we take a look at the one that says it reacted with acid, because it clearly bubbled, I know it reacted with acid. So rock must be powdered to react with hydrochloric acid. Clearly it did not need to be powdered, so it's not dolomite. Then if we look at the one that reacts with stuff here, it's got abundant fossils. I do not see any fossilized shells of any sort in this rock at all anywhere. So that kind of gets rid of fossil limestone and coquina. I do not see miniature spheres in 1 millimeter in diameter like pearls, not at all. White, powdery, feels gritty, reacts vigorously with acid. It's not really powdery, it does feel gritty, but this doesn't say anything about, oh, white. It's not really white either. If I look at this, it says it's chalk limestone. Chalk limestone is literally what you think it is. It's pretty chalky. It's gritty, like they say it is. It powders. You could take it out and draw with it on the sidewalk. Okay. And then we have micrite limestone. It's fine grained, which means that I shouldn't be seeing things like chunks of rock in them. So all these other things don't match. So that's why I'm going to say that I'm actually had a very weak reaction with the acid, except for that one spot, which was super bubbly. Okay. Which might mean that that's actually limestone that's shoved in here too. Okay. Next thing I look at is the grains are visible. Are there no grains? Is it black, lightweight, and smudgy like coal? And is it white, pink, clear, crystalline, softer than the fingernail? So definitely not clear. It's not necessarily whitish or clear or pink. I can't scratch it with my fingernail to get anything to scratch. It's not black, so it's not coal. I definitely have grains, which means sediments. So I have those rock chunks. So my grains are visible. Now we have to figure out, are my grains, are my sediments bigger than these dots on the paper, or are they smaller than the dots on that paper, but still visible is what that says. So they're definitely bigger. I mean, I do have sand particles in here, but I've got some that are gravelly or bigger. So that narrows me down to breccia or conglomerate. So now I have to figure out, are they angular, meaning jagged edges, or are they rounded gravel? So the best one is that first one I pointed out. I see that the edges are fairly rounded. They're not jagged or fresh like a literal point, like on a square. They've been rounded over time. Looks kind of sanded. It's definitely an older particle that's been around for a while and been worn down by friction with water and things like that. So what I actually have here is a conglomerate. So conglomerates are sedimentary rocks that have like gravel-sized pieces shoved in them that are smooth edges. Breccia could very well look like this, but just the gravel chunks that are in it would be not round and smooth edged. They would be fresher and more pointy and jagged. And what I mean by pointy and jagged, I mean these aren't necessarily particles, but if we take a look at my slate, edges on here are very boxy. They're pointy. They're fresh. They're not smoothed over like someone took a sandpaper to it and made them rounded. Or if we look at this marble, while it's got edges, those edges have been worn away over time and they're rounded. So that's all I'm talking about with that. Right. So with that, I think that's what I wanted to get through with this video, is just walk us through the identification process with at least one rock and take the notes on the 3 types of rocks. So next week you will be doing the last 3 worksheet pages in the worksheet packet, and there's one on each type of rock. So there's one on sedimentary, one on igneous, one on metamorphic. And then on Wednesday you will be taking the rock cycle quiz, and that's pretty much it, because I think the last week in school, from what I've gathered, is kind of a catch-up week. Time to redo quizzes, time to get projects wrapped up, anything that maybe you want to need to turn in before the end of the year. So I think I might do a Zoom meeting next week to discuss our projects that we've been doing. I might break it up into smaller sections. Having 60 people join would not work out that well. And that'd be a chance for you to share what you've done and what you've learned. Just give a brief overview. I can do the same for us, and we can go from there. Take care.